Okay, well, good morning, everybody, and welcome. Um, so, oh, see, nothing's working today. Okay, my tablet's not working. So, how was your night last night? Anything going on? One thing I could do, I guess, is spend a lot of time today going over the test, but I don't think I'm going to do that. There's sort of two types of people. There's people who want to go over and think about this test, people who do not and who would rather just move on. And so, to make everybody happy, I've posted some videos. One video. There's two different links there because you can either watch it on YouTube or you can watch it on what's called My Media. And also the solutions are there. So this is on a module in Quarkus. If you scroll down, it's called the Test 1 module, and you can find the test and its solutions. And I just worked through version A, but version B is extremely similar. There's some slight changes to the multiple choice, and that's about it. So before I go on in chapter 5 stuff, anything on anybody's mind that seems like not just a you-specific thing, but a general thing everybody would be interested in? Questions? Yep. Yeah, version C is also pretty similar. Yeah. True. But I'm only posting the solutions for version A. Yeah, true. B and C are similar. Anybody else? Yes, back there. How does the grading work? So, we're going to grade it. So, April right now is going to scan in the back half of your bubble sheet with the written problem on it, and that goes to a system called GradeScope. And then I have some markers that are going to be working on it over the next week or so. And then once that's done, you get a mark out of 8, and then it gets added to your test score. And she clicks a button, and it sends you your written work and how it was graded. So probably about 10 days, 2 weeks, something like that. We'll get that back to you as soon as I possibly can. Good question. Okay. Well, it's going to be a bit interesting because I don't have my tablet pen is not working. So Pius is just ran to get another one. We'll see if it works. But this is sort of where we left off last time, saying that uniform circular motion, the speed is constant, but it is accelerating. And the whole idea here is that if a vector changes, either its magnitude or its direction, then you can subtract final minus initial and get the delta v. And the delta v divided by the time is the acceleration. And that's the whole point of acceleration. So one of the tricks that you see in the book again and again and again is that they just draw a little delta v vector, and they expect you to realize that that's the direction of the acceleration. And that's exactly what's happening here, is that you have, if v final is over here and v initial is over here, then final or initial, I guess, plus the delta v, where's the initial? Delta v equals the final minus the initial. So what she's done here is she's added the final velocity vn plus 1 minus the initial velocity vn. And vn was up and to the left, so you do a negative of it and add it. And that gives you delta v, which is towards the center of the circle. So that's the key here, is that anytime something's going in a circular path, it is accelerating towards the center of the circle, meaning it has some acceleration in meters per second squared, and the direction is towards the center of the circular path. So we need to find that. We need to find an equation for this acceleration. And so I'm going to walk you through some conceptual steps of how to find the this equation. And again, I'm not writing on the slides because my pen is broken, but the slides are pretty good. So And I'm going through what you've probably read in the book. Experiment 1 is that you've got an object moving at a circle at a constant speed, and so the acceleration is towards the center of the circular path. So if you look at this x and this x, that being initial and final, and you subtract final minus initial, you get delta v down like that. Now you take the same circle, but you double the speed. So instead of going, before it was v, now you've got 2v. Well, and you take the same two x's to keep the vectors, I guess the angle's all the same tangents, right? So looking before, what you've done is I've doubled these vector lengths, and so what that does is makes delta v twice as long. So you'd think that that means, here's my other tablet, that's good. Maybe I should unplug this, see what happens. Oh, that's not right. You want to unplug the tablet from the splitter, right? There we go. But the acceleration is the delta v divided by the time. So, and the time is half as much because it's going twice as fast. So you've got delta v is two times bigger. The delta t is half as much. So you're doing like a 2 and divided by a half, you get 4. So what this means is that, doesn't really say here, that if you double the speed, you get 4 times the acceleration. And then similarly, she looks at what if you're going 3 times that speed from the same x's, your delta v now will be 3 times as much because these vectors are 3 times longer, and it'll take 1/3 as much time to get from here to here. So 3 divided by 1/3, you get 9. So this observational experiment is telling you that this acceleration is proportional to the speed squared. So that's important. And then what about the radius of the circle? So we start with, okay, it's going at some speed and some circle of some radius. There's your delta v from these two x's. And then what she does is expands the circle, doubles the size of the circle, but keeps this angle theta the same. And keeps the speed the same. So what this means is that this vi and this vf, vi initial and v final, are in the same directions, because they're at the same angular positions, as they were in this previous slide when the circle was half as big. Because you're using the same angle theta, so they're the same directions, and it's the same speed. So when you subtract them, Pius is working miracles here, you get the same delta v, but the time is going to be longer because it is twice as long. The circle has twice the circumference because it's got twice the radius, so the delta t is 2 times as long. So what this means is that the acceleration, which is delta v divided by the time, will be half as much. So in conclusion, you've got, if the speed is the same and the radius changes, then the proportionality of this little, that little symbol means it's proportional to, the radial acceleration is proportional to 1 over r. And we also know it's proportional to v squared. So combining the two proportionalities, you get v squared over r. And with the constant of proportionality being 1, you got this. I'm not sure where the 1 comes from, but this turns out to be the answer. The radial acceleration is v squared over r. So anytime you're on a circular path and you're going at some speed v, you're going to have acceleration towards the center of the circle, and it's going to be v squared over r. It's a really handy equation. And remember, whenever you have an acceleration, you need a net force. So if I take this orange ball and I swing it around a circular path, then there has to be a net force that's in the direction of the acceleration. Acceleration is AR towards the center of the circular path. So there's a net force towards the center of the circular path here. And that's coming from the string, right? If you let go of the string, then woo, it no longer goes on a circular path. So that tension is providing that force which gives this A sub r. How's this tablet going? You want to try it? Oh, look at that. Once again, I don't know if this is like the 10th time Pius Santiago has saved my ass in front of Connell. Thank you very much, sir. Okay. With a whole new tablet. Oop, that's the wrong pen. That's the crappy pen. Okay, we are doing great. Okay, and we're ready for learning catalytics. Let's think about this radial acceleration. You've got a car that at this instant is traveling a velocity to the east, but it's turning. And the speedometer is at a steady 100 kilometers per hour. So the driver is neither speeding up nor slowing down, but they're turning, sort of steadily turning. So the question is, what direction is the acceleration of the car? I'll give you 1 minute to think about that. Think, pair, share, and then we'll discuss. Okay. Right on. Okay, guys. I thought this one was a little tricky, but let's see what survey says. Maybe give 5 more seconds to click in. First question, and we'll do another question. Go once, go twice. And stop. Laptop 2. Yeah, so I think it's actually directly north. Another good answer was a diagonal west of north, actually diagonal east of north, but neither of those is correct, and I'll try to tell you why. It's because it's a steady speed. What you have to imagine, and I guess it's sort of a calculus concept, is that just a tiny instant before it got to this curve, then the velocity was down in, or whatever, a little bit south and east. And just a little tiny instant after this, it was north and east, a little bit north and east. And so the net is that it just changes velocity only to the north. And another way of thinking of this is that if the acceleration vector has any component which is parallel to the velocity, then that means the car will be speeding up or slowing down. And so when it's exactly perpendicular to the velocity, that's when you've got a constant speed, uniform circular motion. So I think it has to be perpendicular, and since the car's going east, then it has to be exactly north. Make sense? I got one more. Oh dear, where are we here? Yeah. Let's do this one. Well, I got 2 more after this, but we'll take a break. So let's do this one. A ball is whirled on a string in a vertical circle. As it is going around, the tension in the string is A, greatest at the top of the motion, B, constant, C, greatest at the bottom of the motion, and D, greatest somewhere between the top and the bottom. So the trick here is to consider all of the forces on the ball as it's going around, and that includes gravity. Okay. Again, I'll give you 1 minute to think, pair, share, and then we'll discuss. So there's that timer. Let me just do a quick demo of it, I guess, with the ball. Yeah. So it's going around in a circular path. And actually, if I go slow enough, the tension actually goes to 0 even at the top. Whoop. Whoop. You have to go a certain sort of minimum speed to get it going around in a circle with tension. But I don't think the tension is the same the whole time. And in fact, like I say, if I slow it down too much, the string almost goes slack right at the very top. So that's, I think, where it gets to its minimum. Let's go back to the laptop. Actually, we'll go to laptop 2. Going once, going twice. See what you think. Laptop 2. Yeah, so what's the answer here? Greatest at the bottom of the motion. So let me go through why I think that is using my new tablet. So I think that it's greatest at the bottom. As the ball goes around the circle, it must be accelerating towards the center. We figured that out before. A sub r is towards the center. That's the acceleration, and so the net force has to be in the direction of the acceleration. And the net force is just the sum of all the forces that are acting on it. In this case, gravity and tension. So like, let's think about it up here, for example. At point A, you've got, what have you got? You got, I guess, mg acting down, and you've got tension acting down. And so this net force in the radial direction is going to be mg plus the tension, because this is r for the top force, and that's going to be the mv squared over r equals mg plus t, and so t here is going to be mv squared over r minus mg. That sort of makes sense. And then down here at the bottom, you've got that tension is up and gravity is down. And the direction of the acceleration is towards the center of the circle, which is up now. So now you've got the sum of forces in the r direction, which remember is equal to mv squared over r, is equal to tension minus mg. So if you solve for tension, you got tension as mv squared over r plus mg. So here you've got minus mg, and here you've got plus mg, meaning that I think the tension is a lot higher at the bottom. And that's assuming that v, and I say r is the same in both cases, but that's assuming v is the same in both cases, but there's an additional thing. Also, the ball is probably moving faster at the bottom, which would even make it worse, because it kind of probably speeds up as it goes down and then slows down on the way up. So definitely, I think tension is going to be a lot higher for two different reasons when it gets to the bottom. One is that gravity is acting against you, whereas when at the top of the circle, gravity is assisting in this radial force. And then the second thing is that it's probably moving faster, so it needs more radial acceleration when it's at the bottom of the path. Okay, so let's do an actual example. A 0.3 kilogram ball is whirled on a string in a vertical circle of radius 0.8 meters. When at the bottom of its motion, it's moving at 3 meters per second. What is the acceleration at this moment? So what I'm going to do is first sketch it. You've got r is equal to 0.8 meters. You've got, it's down here moving towards the right at v tangent, I guess, is 3 meters per second. See if I can do erasing. Oh, I can't. I'm used to my new thingy here. And then I'm just going to draw over here a sub r is towards the center of the circle. And a sub r, don't forget, is always v squared over r. So it's going to be 3 squared divided by 0.8. So it's actually 11.25 meters per second squared. That's the acceleration. And so Actually, that's the answer to A, isn't it? So, or you could say, I guess, AR is equal to 10 meters per second squared up. If you wanted a final answer or something like that for your test. Then sketch a force diagram, so that's easy. You just say, well, tension is up, and of the string, I guess, on the ball, and the force of the earth on the ball is down. And the acceleration is up. And this is equal to mg, right? And then C is that the sum of the forces in the r direction is mass times A sub r. So it's tension minus mg equals mv squared over r. So tension is equal to, we did this before, plus mv squared over r. It's equal to 0.3. This pen is great, but it's just slightly different. 9.8 plus 0.3 times, we actually did the v squared over r already. Let's just use 11.25 so we don't have to do that again. And I've got 6.315, so the tension is approximately 6 newtons. Okay. Which is a lot more than 3 newtons, which is what it would be if it was just sitting still. When you whirl it around in a circle, you have to have the tension compensating for gravity and also giving it that radial acceleration upwards of the 10 meters per second squared. Okay. So this is this thing about, I'm going to talk about centrifugal force versus centripetal force. So I remember when I was a kid and I was in the back seat with my sister, okay, maybe this dates me, but we weren't wearing seatbelts, and there was these bucket seats in the back, and when they would turn a corner, we would get squished, and I would either squish into her or she would squish into me, and we always felt like we were being pulled towards the outside of the curve. If our parents were turning left, we would get squished over to the right side of the car. So this is a fictitious force called centrifugal force. And actually, although it's fictitious, it's very useful. If you have a centrifuge in a lab, you can put a test tube in it, spin it around, and the centrifugal force will cause sediments to rapidly fall down towards the bottom, like platelets or something like that in blood. So the purpose of centrifugal force is to help describe what life feels like in a non-inertial reference frame. But in reality, in the frame of the ground, what is happening is that there's forces that are centripetal, so towards the center. We call it the radial force, which pushes things towards the center of the circular motion. I think that's so the other thing is this, I told you guys I was going to, so it's not water, it's going to be hot coffee. I went to the second cup. So let's put it on. Yeah, do you want to do the thing? So just to make it even, so the purpose here, you'd think, who would swing hot coffee over their head? But it's me, and the reason is I want to impress upon you that I trust in the laws of physics. Okay, I think I'm right that if I give it enough velocity, it shouldn't spill. So I'm going to, let's take a sip. We're going to maybe pray. No, it's trust in the laws of physics. Am I on the screen there? So I'm going to just place this on the platform. We're well enough away from all the people in the front row, so you should be okay. And we'll just, you ready? Take another sip here. Did you see that upside down coffee? Did even one drop of it spill? That is the power of physics. We'll do it one more time. We'll talk about how that is possible in a minute. Do it one more time. Okay, upside down coffee. Okay. Left one. The minimum speed of water at the top of the vertical path is that at which gravity alone is sufficient to cause circular motion at the top. So that's the kind of idea, and we're going to show that it's square root of g times r. So there's sort of three different situations. If you have more than enough minimum speed, which is what I had in this situation, it's like a roller coaster. So you can imagine a cart going on a circular path, or doing one of these loop-de-loops. If you drive fast enough, then when you're upside down at this exact instant, your velocity is so fast that you don't just need gravity, you also need a normal force pushing down to keep yourself from going in a straight line. This path is so curvy that in order to go in a straight path, you have to be pushed down by the extra normal force. The point is, normal force must always be away from the surface. If you're going too slow, well, you can't, unless there's glue on the wheels or something. Or sometimes, if you look at Canada's Wonderland, you'll see that the wheels are designed so that they're actually on both sides of the track, so they can actually pull. But with most roads or something, normal force can only push, it cannot pull. And it's the same with this string on this platform. It can only pull, right? So if it's upside down, it's pulling towards the center of the circle, and I guess that normal force is pushing on the bottom of the coffee, and the coffee can't go anywhere because, if anything, it wants to accelerate towards the outside of the circle, and so it's all kept in there. I don't know if I'm describing it all that well. This is the exact situation where there's only one force, gravity, and the wheels are just about to leave. And of course, if you go too slow, then you turn into a projectile. You get a parabolic trajectory, and the water falls out and everything. So that's what I'm trying to avoid. So going back one slide, let's put this on here. This is when so again, we're going to say the sum of all the forces is equal to mv squared over r. And this is just equal to, I guess, just mg in this case. And you can just solve for v. And you could divide both sides by m. And you can say that v squared is equal to g times r, and v is equal to the square root of g times r. So that's where that minimum comes from. Okay. And that's when it's less. So let's review a little bit of these as-needed forces and see where we are. Time-wise, we're doing pretty well. Okay. So this is going back to these as-needed forces, the self-adjusting forces, I kind of call them. So the ones that are not included is gravity and kinetic friction. Those have nice equations. Remember, the normal force, the tension, and the static friction, these are the ones that self-adjust according to the situation that you find yourself in. Usually the acceleration is found somehow. So normal force is whatever is needed to keep you from crashing through the surface. Okay? Tension is whatever is needed to keep the string from breaking. And so you can imagine they must have maxima as well. If you pull a string too much, it'll snap. And if you put too much weight on a table, the table will break, right? Static friction has a nice little handy equation that people use for the maximum, but it is very similar to the tension and the normal force in that it just self-adjusts. And you only need it if you need it. So in all these cases, what you do is you draw a force diagram, and you write down Newton's second law, sometimes in your x and y coordinates, or if you're doing in a radial thing, you do it in your r and t coordinates, which is just like x and y, except t is tangent to the circle and r is towards the center of the circle. So let's do a couple more learning catalytics, and then I'll do an example, and I think we'll be done. You guys are probably a little tired, some of you. I'm a little tired. Let's do this one. Here is a car going over a hill. And what I want you to think about is the comparing mg, or fg, the force of gravity, to the normal force of the road on the car at this instant. Give me a minute to think about that. It was a late night last night. We were counting tests. I just want to sit down for a second because I want you to think about what the normal force feels like. So when you're sitting in a chair as you are, you're actually experiencing a normal force as you would in a car or something, and it is an upward force on you. And if it were taken away for some reason, like someone was to take the chair out from under me, I would experience weightlessness and kind of start to fall, right? So let's answer this. This is a tricky one. So I'm going to give you 5 seconds. Going once, going twice. I really wish I could get rid of the color coding on this. I need like black and white or something. So unfortunately, I have to show you the answer when I show you the vote. This is sometimes when I would say it's either B or C. Okay, it is B. But people were really split on this one. And so the way you do it with the physics reasoning is straightforward, which is you say, okay, hello. Sure. Yeah, perfect. So you say, what's the circular path? Well, the circular path is this one. There's the circle. It kind of goes below the screen, right? But the center of the circle, center of circular motion. So that's the first motion. The first step is just figuring out if you were to go towards the circle, accelerate towards the center of the circle, which way would you accelerate? Well, you would accelerate downwards. A sub r is down. Is v squared over r, downward. So again, system here is you. Maybe you in the car is the car, I guess. You've got normal force acting up, and you've got mg acting down. The sum of all the forces is equal to m in the r direction is equal to, so r is down here, is ma sub r. So it's going to be, mg is actually down in this case, right? And mg is down, but it's positive because I've defined plus r down. mg is positive because plus r is down. Why is plus r down? Because it's towards the center of the circular path. And you're on a vertical circle when you're going over a hill for which the center of that circle is below you. So you do mg minus the normal force, because the normal force is up, is equal to mv squared over r. So what that means is that this f, whatever, normal, solving it for normal is equal to mg minus mv squared over r, and is less than mg. So that's why I like B there. And what that feels like if you're in the car going over the bump is that all of a sudden the force on you is reduced. And so you feel a little weightless. And this used to happen, again, when I was a kid in the back seat of the car. I remember in Edmonton, there was this, I don't know what was under, there was a subway or something, so there was a little bump in the road. and my stepdad would hit it, and he would just really go fast, so that when we went over the bump, we would like feel a little weightless as we were going over the top of it, and we would laugh like crazy. So that's what weightlessness feels like, is that normal force is reduced. Let's do another learning catalytics. So the next one is, what about a valley? same question. Give you a minute. Should I explain your reasoning to your neighbor? Should understand both of these, not just that they're opposite, but are we good? Oop. Go once, and twice. And you can see if the other one was sort of good. Okay. Yeah, so basic idea, I think you've got it, is that in this case, the center of circular motion is up. So if you draw a circle that goes through there, this is the center. So finding the center of the circle is your first step of a circular path. So anytime you're on a circular path, there's a center to that circle, and you define plus r to be towards the center of the circular path. So in this case, when you do that same, the sum of all the forces in the r direction is equal to mv squared over r. Now, normal is positive, and gravity is negative. So you do n minus mg is equal to mv squared over r. Okay? And then when you solve that out, you get n is equal to mv squared over r plus mg. So it's greater than mg. Okay? All right. Okay, so next thing is banked curves. So this is again a favorite thing that comes up on physics tests, but I think it's kind of interesting and important, which is you're going around a highway curve of some radius, and it's banked at a 15-degree angle. So there's a sketch here. So in my sketch and translate phase, when I do these banked curve questions, I sort of have to draw the sketch twice. One from a bird's eye view to sort of show the circle and where the center of the circular path is. And the other, I have to do it like kind of a rear view, like from the side, watching the car go away. Now, I can't draw things in 3D. I only draw in 2D because I can barely even do that. So if something's in 3D, like circular motion often is described that way, you just draw it twice from two different angles. So this is the same thing. You can imagine a circular path. Doesn't show the whole circle here, but that would be the center of that circular path from above. And then the rear view, you're looking at that same car, and now, like the circle is just, it's like in the line of sight. It's going into the car or something like that. This is the 15 degrees into the page, right? So it's, once again, constant speed. So that helps. v0. And it's on a circular path, so I can already tell you exactly what the acceleration will be, which is that a sub r is equal to v0 squared divided by r. So that's good. Without friction, without assistance from friction. Is that even possible? Let's see. So if we do without friction, whatever that means. There's just, so I told you that there's static friction, which can accelerate a car. We're going to set static friction equals to 0, which actually, since it's as needed, then this makes sense, right? If there's no static friction needed, it can go to 0. So, and we'll also just define the system as the car. And R is equal to the road. So the force diagram is going to be, here's the car. Let's do, so actually, here's the big question. Should you do the force diagram with the top view or the rear view? And I'll tell you, with lots of experience, it's rear view. You should do the force diagram in the rear view, because gravity is important, and it's really hard to draw the gravity force on the top view. It'd be into the page. So let's do rear view. And in that case, the force of gravity of the Earth on the car is down, and you've got the normal force, in this case, is acting at a little angle, normal force of the road on the car. And then friction, oh, there's no friction. Weird. I'm not going to draw friction because it actually says frictionless, but there's the surface anyway. So it's a strange question, but let's see if we can solve it. So imagine if it was just an icy banked curve. Maybe you could do it as long as the road was banked upwards. Assume only forces are normal and gravity. Okay. So, and then I have to find the direction of all this stuff. What I'm going to do is define, so this is the acceleration a sub r. So let's define plus r this way. And the t is kind of weird. It's into the page. So I'm not going to define up to be t. Let's define just up to be y, actually. Plus y is up, because that's like vertical. So it's weird. I've got r going towards the center of circular motion. T, I don't care about. It's going tangent into the page, and y is going up. So now I have to get my components. Normal's on a diagonal, right? So here, let's try to figure out this actual theta. So if that's theta, and that's normal, this is going to be theta right here. And so if you do vertical here, then this is 90 minus theta. And so this is theta. So that means if I was to draw a right angle triangle here, here's your normal force, here's n in the r direction, and here's n in the y direction. Oh, sorry, y. So it's acting up, and there's theta. So I'm just dividing your normal force into components. And so I've got n sub r is equal to n sine theta, and n sub y is equal to n cos theta. And a sub y is equal to 0 since it's not accelerating up or down. It's only accelerating towards the left in this diagram. Okay. So let's do this. I think what I'll do is just try to sort these things out into components. You've got normal and FG. And let's do the R components. Let's make a little table. And the Y components, and then we'll add them up. So the normal we said was sine n sine theta and n cos theta. What time is it? Yeah, we've got 4 minutes. We can finish this. The gravity doesn't have an r component because it's acting straight down. It's just negative mass of the car times g. And I know that a sub y is equal to 0. So that means that the sum of all the forces in the y direction is 0. And that's going to be n acting up, n cos theta, minus mg. So that means that n is equal to the mass of the car, let's call this the mass of the car, times g divided by cos theta. And then what we'll do, so have that equation, and we'll plug that into, up here, a sub r is the sum of all the forces in the r direction divided by the mass of the car, which equals n sine theta is the only r component force divided by m. Plug this into right here. And you get m g sine theta divided by m cos theta. And the m's cancel at this point. So that's lucky. And you get that the a sub r is equal to g sine theta over cos theta. And that's equal to v0 squared over r. And you just solve for v0. Solve for that needed speed so that you can go without friction. So v0 squared is equal to g times r times sine theta divided by cos theta. So v0 is equal to square root of g times r times sine theta divided by cos theta. So it's equal to 9.8, square root of 9.8 times 70 meters times the sine of 15 degrees divided by the cos of 15 degrees. So I got 13.56 meters per second squared. So V0. If you go at 14 meters per second, then there's no longer any friction, static friction needed to keep you on the curve. You can go around, but you have to hold that exact same speed. If you go a little slower, then they'll start to slide down the hill. If you go a little faster, you start to slide up the hill. But if you stay at just this exact speed, you'll go around at that nice velocity, or at that nice curve. So I do want to talk about gravity that's out in space. This is one of the astronauts, Jessica Watkins, who's up there right now. You can go on her Twitter feed if you want. But something to consider is that the radius of the Earth is 6,400 kilometers. And right now, the International Space Station is 500 kilometers up. So are astronauts really weightless? And we'll talk about that when we come back. Certainly she's floating around. We'll talk about that on Friday. See you Friday.